Welcome to the SaberRD online training course. This series of fast-paced videos will teach you the full power of the SaberRD simulation environment. In this section, we explore stress analysis. Component stress. It threatens system reliability and shortens product life. Understanding and managing component stress creates a robust design. Saber's stress analysis automates the process with a few simple steps. We specify maximum ratings for the components, enable stress calculations, and run analyses. The result is a tabulated stress report. Let's show how to run stress analysis with this AC to DC converter. We'll create an experiment to automate the process. We open the Experiments pane, click the New Experiment button, and give it an identifier name. Stress can be calculated with operating point, transient, and DC sweep analyses. Clicking the Transient button adds the analysis to the canvas. We change the end time to 50 milliseconds. To view the output waveforms, we define a graph container. To this graph, we add a signal for the output voltage and one for the load current. We test our simple experiment by going to the Simulation tab, where we select Experiment from the pull-down and the experiment identifier we just created. Pressing the green Start Analysis button runs the simulation. We see an output that settles to 12 volts. At 25 milliseconds, the load increases. This additional load will further stress the components. Now it's time to specify the ratings for the components. Most generic parts have unspecified ratings when first placed on the schematic. Since this design uses generic parts, we need to specify the ratings for the ones for which we want to monitor stress. For example, let's look at the properties of R1. Its ratings parameters are in this structure. We can edit them by clicking on the ellipsis. We set the maximum power to 1/4 watt. In a similar fashion, we add ratings to the other components for which we want to monitor stress. It's time to add stress analysis to our experiment. We do this by modifying the transient analysis task. In the Properties pane, we scroll down to the stress options. We change the Run Stress Analysis switch from No to Yes, using the pull-down selection, and do the same for the Generate Stress Report switch. The Stress Measure list lets us select which components to monitor for stress. The default is a wildcard specification for all components. We'll revisit the derating file in a few moments. The minimum stress to report is a percentage floor. For example, 20 means to report only those components stressed above 20%. We'll leave it at its default of 0%. Let's run our experiment again with the stress monitoring enabled. The results now include a stress report. We open it by double-clicking. The first page shows a summary. Using the page arrows, we see the rest of the report is a table, itemizing the stress applied to each component during the transient simulation. We see columns for the instance, stress parameter, rating, maximum value, at which simulation time the event occurred, and the stress ratio. The stress report can be exported to a wide range of formats. Derating is a common tactic of stress analysis. Most component ratings are limits specified by the manufacturer, but many times a designer may wish to shrink the safe operating areas to extend the life of the components. Derating is done within Saber by using a text file. The syntax of this file is explained in the Saber user manual, but it is best illustrated by an example. The lines beginning with a pound sign are comments. Each line is a specification with 5 fields corresponding to the instance path, part type, part class, rating parameter, and the derating value. Wildcards make it easy to derate a large set of components. Note local specifications override the more global ones. Let's add the derating file to our experiment. We select the Transient Analysis task and specify the derating file in the Properties pane. We run the experiment again and open the report. The summary indicates it used the derating file. Inspecting the stress table shows how the derating values and stress ratios have changed. The simulation shows some parts are overstressed, while others operate close to their limits. With stress analysis, we identify hotspots and take corrective actions early, ensuring reliable operation and a robust design. This concludes this section of the SaberRD online training course. To download a free student version of SaberRD, go to the Synopsys website. To further your understanding of this material, go through the lab exercises found at the link listed in the description of this video.